Imagine signing a legally binding contract without ever touching a pen. No ink, no paper, not even being in the same room. And yet, that signature is verifiable, it's tamper-proof, and it's absolutely secure. Now, this isn't science fiction. This is the invisible system that underpins almost all the trust we have in our digital world.
So let's get right into it. How can a bunch of numbers possibly replace something as personal, as trusted, as a handwritten signature? How can we prove something is authentic and hasn't been touched when it only exists as data? Well, the answer isn't a picture of your name. It's a really clever system of digital keys and pure mathematical proof. Let's break it down.
Okay, first things first, we have to clear up a huge misconception. When we talk about a digital signature, we are not talking about a scanned image of your handwriting. It's not a fancy font, and it's not something you squiggle with your mouse on a screen. A true digital signature, well, it's something way more profound. It's pure cryptography.
To really get this, we have to forget about signatures for just a second and focus on the bedrock of this whole thing. A brilliant system built around a special pair of mathematically linked keys.
This system is called public key cryptography. Here's the core idea. Every person gets a pair of keys. Now, these aren't physical keys, of course, they're just long strings of data. But they're bound together by a really special mathematical relationship. Whatever one key locks, only its partner key can unlock. And whatever one key signs, only its partner can verify. That relationship, it's the key to everything.
So, the crucial part is how these two keys are used. Your public key is, well, public. You can share it with the whole world. People use it to verify things that come from you. But your private key, that's like the key to your deepest, most secure vault. You have to keep it absolutely secret, because that is the key you use to sign.
All right, so we've got our keys. Now let's put them to work and see how this cryptographic foundation actually builds a signature. So the first weird thing is, we don't actually sign the document itself. Instead, we create a unique digital fingerprint of it. And we do that using something called a hash function. It's an algorithm that can take the entire document, no matter how big, and condense it into a short, totally unique code.
Just think of it like this. The whole document goes into a machine on one side, and out the other side comes this one-of-a-kind digital fingerprint, or hash. It perfectly represents that document at that exact moment in time.
And here's the magic trick. This fingerprint is incredibly sensitive. If you change just a single comma or a period in that original document, the hash doesn't just change a little. It becomes completely different, totally unrecognizable. This is called the avalanche effect, and it's what makes even the tiniest bit of tampering instantly obvious. So here's how you sign something. Step 1, you create that unique hash from the document. Step 2, you take your secret private key and you use it to encrypt that hash. And that encrypted hash, that is the digital signature. Finally, you just attach this signature to the original document and send them both on their way.
Okay, now for the moment of truth, verification. When your friend gets the file, they do a kind of parallel process. First, they take the document you sent and run it through the exact same hash function. This creates their own version of the hash. Second, they take your digital signature and use your public key, the one you shared with the world, to decrypt it. This reveals the original hash you created way back in step 1.
And this is the final, critical step. Your friend compares the hash they just made from the document with the hash they just decrypted from your signature. If they match perfectly, two incredible things are proven at the exact same time. 1, authenticity. Only you, the owner of the private key, could have created that signature. And 2, integrity. The document has not been altered, not even by a single bit, since you signed it. It's not a guess, it's mathematical proof.
Now, this system is incredibly secure, but you might have spotted a potential problem. If anyone can just create a pair of keys and say, "Hi, I'm your bank," how do we know who a public key really belongs to? In other words, who verifies the verifier?
Right. How can you really trust that the public key you're using for your bank actually belongs to your bank and not some clever imposter? Without some kind of trusted anchor, the whole system could fall apart. And that anchor has a name, a certificate authority. A certificate authority, or CA, is a highly trusted organization. You can think of it like a digital notary for the entire internet. Their whole job is to verify identities. They investigate a company, and if it all checks out, they issue a digital certificate that officially binds a specific public key to that verified real-world identity. This creates what we call a chain of trust. See, your web browser is already programmed to trust a handful of major certificate authorities. Those CAs then verify a website's identity and issue it a certificate. And that certificate is what vouches for the public key that's used in the digital signature that secures your data. It's like a cascade of trust, all starting from one reliable source.
So we've gone from these cryptographic keys all the way to global chains of trust. But let's zoom out for a second. Why did we build this incredibly complex, invisible system? Why does it matter so much? Because digital signatures are absolutely everywhere, silently protecting you every single day. Every time you download a software update from Apple or Microsoft, a digital signature is what proves it's legitimate and not some piece of malware. They secure your financial transactions, official government documents, legal e-contracts, even the core integrity of your phone's operating system relies on them. Without this system, our digital lives would be chaos.
But the story doesn't end here. The very math that makes all of this work is actually threatened by the theoretical power of future quantum computers. So right now, a new kind of arms race is happening, as cryptographers design brand new post-quantum signatures to make sure this chain of digital trust stays unbroken for generations to come.
So, what's the big takeaway here? In our digital world, a signature is so much more than a replacement for ink on paper. It is cryptographic certainty in a world full of digital uncertainty. It isn't just a signature, it's proof.